Okay, so now we're ready for some more memory list work, but this time memory list for integration. Okay, so let's make sure we remember some of these, and we'll throw in a few specific examples. Okay, so I'll write it and you see if you remember it. This one should be x to the n plus 1 over n plus 1, and we should always remember to tack on our plus c. If it's an indefinite integral, any constant could be added on because when we take the derivative, the constant goes away. So let's do a couple specific examples of that. Let's do the integration of, so try to work through these examples. Let's do, okay, so you have a list of examples there. Let's review them. Pause if you haven't had a chance to try to work them out yourself. Okay, the first one, oh, I forgot. Oh, no, I have it in there. It's hidden now. Let's slide that down so we can see the n plus 1. So this one is pretty straightforward. You just raise it by 1, and 2 plus 1 is 3, divided by 3. So integer exponents are easy. This one, you need to remember that this is really the integral of x to the 1/3 dx. Just quick review. If you want to add 1 to 1/3, you want to call 1 3/3. So always convert 1 to a fraction where it matches the denominator. Okay, so let's see, get an answer. Let's go back to red here. We're going to raise that 1 and we get x to the 4/3 power over 4/3 plus c. Get this out of the way. That's if we strictly use the formula. I think most of you are comfortable going right away into the idea that instead of dividing by 4/3, we'll take 3/4, and then we'll have x to the 4/3, and that would be another way of saying that. Let's just leave it as x to the 4/3 plus c. It would be x plus the cube, or times the cube root of x, but for now we'll just work with x to the 4/3 because often we're going to then put this into the fundamental theorem and do something like evaluate from 0 to 1 what the cube root of x dx does. So rewriting it algebraically may or may not be that helpful, and it's time consuming. So we won't rewrite them, we'll leave them as powers. This one would be x to the negative 1/3 dx. Be careful, you're adding 3/3 to negative 1/3, so that's x to the 2/3 when you raise it, and most of you are comfortable with, instead of dividing by 2/3, multiply by 3/2, get you to the answer faster. This one, that's x to the negative 2. Be careful, a lot of people will lower it 1 instead of raising it 1. When you have negative 2 and you add 1, you're at negative 1. So this becomes x to the negative 1 over negative 1. But we usually, instead of dividing by 1, we'll multiply by, instead of dividing by negative 1, multiply by negative 1. And this one, it's helpful to write algebraically as negative 1 over x plus c. The last one, when you try to do this, you hopefully realize it doesn't work. All right, so this is the case that doesn't work, and we'll come back to it in just a moment, because if you raise by 1, you get x to the 0 over 0, and we're not allowed to divide by 0. So this is the case that doesn't work for the power rule. Any other case works, but not that case. Okay, so whenever you run into division by 0 using the power rule, you know you're working with this special case. We will come right back to that in a couple of minutes. Okay, so other ones that you should know. This is just as easy backwards as it was forward. Hopefully you knew that was e to the x plus c. Let's get into our, let's do the inverse of this right away. Okay, so we actually don't know how to do ln of x, so we're going to put that on hold, but just bringing this one case down that we already knew. We knew that the derivative of ln of x was 1 over x, so the integral of 1 over x dx is in fact the natural log of x with absolute value signs plus c. Whenever x is positive, you don't need to put the absolute value signs in, but you do need to keep them in there in general if we're worried about all possible cases. All right, let's keep moving up. So once again, this is the one case that fails in the power rule, so you need to know that its antiderivative is the natural log. All right, so we have e to the x. Let's go to our trig functions. And let's write okay, these are the ones you really need to know. So if you look at these, the negative cosine of x plus c, hopefully you knew that this one was the sine of x plus c. You forget, memory wheel, sine goes to cosine to negative sine to negative cosine when we take derivatives, but now for integrals, we go the other way. So that's what's going on here. We're going backwards on our little memory wheel to go the other way. So you must know those. Others that you must know that come up a fair amount. You need to know that that is the inverse tangent of x plus c. Oops, I left off the dx. That's similarly grouped. Inverse sine of x plus c. By the way, you don't need to know the one with a negative in there, because if there were a negative, just switch colors here. If I were to do the negative of this, you should know that the derivative of inverse cosine leads to that integrand. So this would be an inverse cosine of x plus c, but the negative sign could have factored out, so this must be the same as, let's call this c1. We don't know what that constant is. It's the same as the negative of the inverse sine of x plus c. Well, inverse cosine and inverse sine don't look exactly like, they are vertical shifts of each other, so if we pick our c carefully, it really ends up being the same result. So you don't need to know both of those, you just need to know the positive of that. And then we should have some of these memorized because of the derivatives. You should realize that integrand was the derivative of the tangent, therefore that would be true. You should recognize that integrand as the derivative of the secant. Okay, and then we have the cosecant squared of x dx. You should realize that's almost like the secant squared, so it must almost be like the tangent. It is the negative of the cotangent of x, because the derivative of cotangent was negative cosecant squared. And then finally, that looks a lot like the one for secant, that was right up here, because it is the cosecant with a negative sign. If I had a negative in that integrand, that would be exactly the derivative of the cosecant. Therefore, its antiderivative must be the negative cosecant. You won't see that one come up very often. The ones you will see this come up. Well, let me change colors. You will see this come up a bit, and you will see this will come up a fair amount, and then everything up above this comes up a lot. Okay. Now, there are a couple that are a little more subtle. Are if I wanted to do, these are kind of on the memory list. We should know how to do the antiderivative of the tangent of x, right? If you forget it, you can rewrite it as the integral of sine x over cosine of x dx. And then you want to do some u substitution. Okay. It's better to substitute for the denominator because the derivative of that so if we do a little bit of rearranging, I can say that I'll do it in method 2 here. Du is negative sine x dx. So dx is equal to du over negative sine x. So we can rewrite this as negative, the integral, the sine x will cancel out. I brought the negative out front already. So that cancels out, and we have a du over u, or if you like, negative integral of 1 over u du. You should be comfortable either way. So that has to be equal to negative ln of absolute value of u. And therefore, since ln, or since u was cosine of x, this is negative L of plus a c, negative ln of absolute value of cosine of x plus c. You'll see that in the book on the memory list, as well as that for the integral of tan x. I wouldn't expect you to have that memorized, but you shouldn't be shocked when you see that pop up occasionally. So some of these things on the memory list, if you come across them on the homework and they're one of these more, this is infrequent, remember the back of the book has the whole list. So if you come across a more infrequent one, just look it up in the back of the book. Everything that I have starred above, you should know how to do power rules. As you should be able to integrate power rules, certainly e to the x, certainly 1 over x, and certainly the sine and cosine. You need to have those at your fingertips and be able to use those all of the time. If you're looking those up, you're going to slow yourself down a lot.